Let's talk about vectors. So there's like, oh, let me maximize that. Sorry. Gonna go away. Good. All right. Vectors. So there's probably like 3 or 4 different ways people like to write vectors. Let me show you a few of them. So let's say the vector v, which usually you write a little arrow over it or a half arrow. I'm going to say the vector is, my preferred notation is probably like this with, I don't even know what you call those, brackets. Those are also called brackets. I know we're not very original in math. We call all things the same thing because why not? So you write it like this, and that vector really just means you're going 3 in the x direction and 4 in the y direction. So you're starting somewhere, usually at the origin, although you don't have to start at the origin. And we're going 3 to the right, 4 up. So the vector starts there, ends there, and there's your vector v. Starting at the origin, ending at the point 3, 4. But you could literally draw that vector anywhere else in space or in the plane, and it would be the same vector, as long as it went 3 right and 4 up. So I could also draw it, annoyingly, maybe it's like starting right here and going over there. Right, that is also the vector v. They are the same. They're not like similar or congruent or whatever. They're actually the same thing. Doesn't matter where it emanates and where it ends, as long as it has the same direction and the same length. That's what defines a vector. Its direction and its magnitude, aka its length. Okay, so let's say a few things about notation. So here are some other ways to write this, which your professors will probably go back and forth between annoyingly and never be like, yeah, this one or this one, this one. So here are at least 2 other good ways. You might write it as a column vector like that, 3, 4. You might write it, yeah, I really hate this notation. You might write it like this, which I really don't love, but some people like that. I don't like that. I'm not going to write them like that. I would always pick this over that because this is pretty standard book notation. And then probably the other preferred one is 3i plus 4j. And what we're really doing there is we're using the basis vector, or I should say the standard basis vectors, I equal to the vector 1, 0, so the unit vector in the x direction. J is the unit vector in the y direction. If you have questions, don't hesitate. You should ask them. I mean, I know I'm going to say a lot of things, but like, so you might be getting ahead, but that's fine. If that happens, I'll just say it. This is the unit vector in the x direction. This is the unit vector in the y direction. So what you're really writing there is you have 3 times the vector 1, 0 plus 4 times the vector 0, 1. For those of you, I think in Alvarado's class, there are some questions about writing some vectors as the sum of some as linear combinations of basis vectors. That's what he means. You would take this vector and just write it as 3i plus 4j. It's no one would ever think of it that way. Really, everyone would just be like, oh yeah, you're just writing the vector another way. We might as well talk about 2 and 3-dimensional vectors because that's what we're dealing with here. So another example. Ooh, do I want to draw that? Yeah, I kind of do want to draw that. And we'll get there in a minute. Let's talk about this one. So this vector v, its magnitude, so the magnitude of v is, we either use this symbol, which looks like an absolute value, but since it's an absolute value of a vector, we say it's the magnitude or the length, or we use double absolute value symbols to mean the magnitude. That is going to be the length of the vector. Which you know how to find, it's really just the distance formula. You're starting at 0, 0, you're ending at 3, 4. You have a right triangle. It's going over 3 and up 4. You're trying to find the hypotenuse of that triangle. We could do all the math, but really it just ends up being that the magnitude of v is equal to the square root of the first component squared plus the second component squared. Or however many components there are. If it was a vector that had 3 components or 4 components or 5 components or some n number of components, it would still be the same calculation. The square root of the sum of the squares of all of the components. And we'll say more about that in a minute. So this vector would have a magnitude of the square root of 25, which is 5. I usually prefer this notation because it's less writing, but you should think of these notations as being interchangeable. If you see absolute value of a vector or double absolute value of a vector, they mean the same thing. They just mean how long is that vector. Okay. I'm going to keep going. If you have questions, you should say things. Hopefully you've seen some of this already in your respective classes. Let's talk about an example. So let's find the vector from point A to point B. Point A, which is going to be the point 2, -3, to point B, which is going to be the point 6, -8. Sure, why not? Well, that's an 8. Yeah, sure, that's an 8. We can buy that. Okay, there's a couple ways to do this. So actually, I could draw it first. So we're starting at the point 2, -3. I give myself a lot more vertical room than I needed here. 2, -3. I'm not being particularly exact here. I'm just kind of approximating where it is. And then 6, -8 is maybe like down there. And the way we find the vector that starts at A and ends at B, or you could say originates at A and terminates at B. There's probably other fancy language you could use. The vector AB, written like that, is the vector where you do the B coordinates minus the A coordinates. So the coordinates of B, so the X coordinate 6 -2, and the Y coordinate -8 minus -3. And so I end up getting 4, -8 plus 3 is -5. Which makes sense as far as how the picture looks, right? This vector definitely should be going right and down. And it does. If we start here, we're going right and down. The magnitude of this vector is just going to be the square root of 4 squared plus -5 squared. Which isn't going to be very nice. It's going to be some irrational number. It's going to be the square root of 16 plus 25, which is the square root of 41. And that's as good as it gets, right? That's the magnitude. I can't do anything else with it. A question that often gets asked kind of annoyingly is to find a unit vector in the same direction as your original vector. And the reason we ask this really is because later on, you're going to get asked questions in the beginning of 17C about like, find the direction of something. Usually like find the direction of maximal increase of this function, which is something you'll get to later. But the point is, there's lots of correct answers to that question, right? I want to point out that all of the vectors I'm about to write point in the same direction. The vector 1, 2, the vector 2, 4, the vector 3, 6. All those vectors, I should give them different names. Sorry, let's call that one V. Let's call this one U and this one W. Sorry, I meant to call them different names and got too excited. So the vector V over 1 and up 2, there's V. But the vector U over 2 and up 4, those vectors have the same direction or the same maybe slope if you wanted to think of it that way. Right, there's the vector U. And the vector W over 3 and up 6, also, I mean, not surprisingly, points in the same direction. So there's W, which is much longer than U and V. Well, not much, but like it is longer. The problem is someone might ask you, what direction does the thing point in? And all these answers are technically correct. They all point in the same direction. But we want to have a uniform answer, especially if you have a class with web work. Your teacher is not going to want to have 1,000 different answers all be correct. So what we do is say, well, the way we can make so everybody has to give the same answer is by saying that everyone's vector has to have the same length. Everyone has to give a unit vector, meaning a vector of length 1. It's not hard to make a unit vector out of a vector. All you do is divide the vector by its own magnitude. So if I wanted a vector of length 1 called a unit vector in the same direction as AB, we would just take AB and divide that vector by its own length or by its own magnitude. The process is called normalizing or unitizing a vector. Although unitizing is not something people normally say, it's kind of a weird word. So here, the unit vector would be the vector AB divided by the magnitude of AB, which in this case is the vector 4, -5 divided by the square root of 41. And again, if it were me, I would probably choose to actually write it as 1/√41 times the vector 4, -5, because to me that is the least annoying way of writing it. But people often distribute that to each of the terms in the vector and write it as component-wise 4 over the square root of 41, -5 over the square root of 41. And for whatever reason, we typically do not rationalize these. You can, it's totally fine to rationalize them, but people don't really feel the need to. All right, questions so far? I know I've said to ask questions, but like we still. Okay. Can I manage these papers here? Maybe. All right, let's look at some more things. Unless there's questions. Actually, not some more things. I'm gonna give you a problem to do. So I want you all to find the vector from point A. Let's use different points from point C to point C. From point C. Well, from point C to point C would be the 0 vector. If you started in the same point, and there is such a thing, a 0 vector is kind of annoying. It's a vector that literally has 0 length, which is, it is important, but okay. Let's say we want to find the vector that emanates from, I don't know, the point C, which is at 1, 3 to the point D, which is going to be, I don't know, 13, -2. Find that vector. Then after you found it, find the magnitude of it. And then finally, find the unit vector in the same direction. tell you that the magnitude of the vector is a nice integer number. The square root of 169 is 13.
What was the square root?
I forget there's a little clock right there. I'm dumb. Most I had to look at my watch and be like, let me give you 45 seconds to work on this problem. There's literally like a little timer right there. And I didn't say that. Okay, let's go ahead and find the things. So the vector from C to D is going to be 13 minus 1 in the x coordinate, -2 minus 3 in the y coordinate, x, y, I, j, whatever people would say, right? The first and the second. That's going to be the vector 12 comma -5 or 12i minus 5j. Those are both good ways of, oh yeah, those are, yeah. I would really stress becoming comfortable with going back and forth between these because people are going to do it all the time, myself included. Sometimes it's more convenient to write it that way than to just write it that way. So the magnitude here, the magnitude of CD is going to be the square root of 12 squared plus -5 squared, which is the square root of 144 plus 25, which is the square root of 169, which is 13. The magnitude of a vector is always non-negative, right? You can't have a vector with a negative length. It's always a positive length. Square roots always give you positive numbers. And then finally, the unit vector, you're just taking the vector and dividing it by its own length. So the unit vector u in the same direction is going to be the vector 12 -5 divided by 13. Here, since the denominator is an integer, I probably would usually distribute it and write it as the vector 12/13 comma -5/13. Or if you prefer, 12/13 I minus 5/13 j. Okay. More things. Keep it on going. I'm sorry, I can leave that there. Sorry. Okay, let's look at a couple of vectors here. So vector addition and subtraction. The thing I'll say about vector addition and subtraction, and also just because it's coming up in the not too distant future, matrix addition and subtraction. When you're adding two vectors or adding two matrices, they have to be things that are the same size. Meaning you can't add a vector that has 2 entries to a vector that has 5 entries. They aren't the same sort of thing. Likewise, when you're adding matrices together, they have to be the same size. If you want to add a 2x3 matrix to another matrix, it also has to be a 2x3 matrix. And then the nice thing about vector addition and matrix addition or subtraction is that you add things the way you think you should, meaning you add the like components together. So if I'm going to take these two vectors, let's use v equal to 3, 1 and w equal to 2, 5. The way you add v plus w is the way you think you should add v plus w. You add the x components together and you add the y components together. So we're also going to draw them, but let's first write it out. So v plus w is just going to be 3 plus 2 in the first component, 1 plus 5 in the second component, which is going to be the vector 5, 6. Vector addition does have a nice graphical representation. If you draw these vectors, I have to make sure I give myself enough room here. This is where you actually do have to be pretty kind of like drawing all your little marks here so you can do stuff. So that should be enough. So first I'm going to draw the vector v, although it doesn't actually matter which one I draw first because it doesn't matter which order you add the vectors in. You can do v plus w or w plus v, just like most addition works the same either order. So I draw v. V is the vector over 3 up 1. And sorry, when I say over, I mean right? If I say over, I'm going in the positive direction. So over 3 up 1, there's your vector v. And then from v, I'm going to draw the vector w. So the vector w is over 2 to the right and up 5. So over 2, up 5 lands me about there. And the resulting vector that starts there and ends there is the vector. Let's get a ruler out so I make sure not to screw it up here. That is the vector v plus w. And it exactly starts at the origin and goes over 1, 2, 3, 4, 5 and up 1, 2, 3, 4, 5, 6. As it should, because right, we went over 3 and then up 1 and then we went over another 2 and up another 5. So in total, we went over 5 and up 6. This also kind of shows us why the triangle inequality is true. I know on the Goldsmith homework I just looked at, there's something with the triangle inequality there. The triangle inequality literally says that if you take 2 sides of a triangle and add them together, they add up to more than the third side, which seems reasonable, right? If you add the lengths of these 2 sides together, is it going to be more than that side? I think so. Let me show you. Actually, I think this is worth this. This is not super duper important, except unless you have homework. But let me draw this picture again, kind of this way. Kind of my picture. Okay, fine. I want to point out that these 2 sides here, let's call them A and B for a second, have to add up to more than C. And the reason why is because if I kind of just swing this down like that, well, there's your length of B. And if I do the same thing to the oops, do the same thing to the other one, swing that down, there's your length of A. And certainly A plus B is more than C. And that's true for any 2 sides. Obviously, it makes sense to, obviously. The only really thing you have to check is if the 2 shorter sides add up to being longer than the bigger side. So that's kind of what the triangle inequality is getting at. Showing it's true is not inconsequential. We'll circle back around that a little bit later, but it is something that is true. And actually, surprisingly, okay, not a huge deal, but I just want to say one thing. This fact comes up in a lot of higher mathematics classes. Like this triangle inequality is used to prove a lot of important things in math, which might not seem like really this kind of not that big a deal looking thing. Yeah, it's kind of important. It comes up all the time. Anyway, side note aside, let's look at one more thing here. Let's say I wanted to find 2 times v minus w. Well, I can do that same sort of way I did the first thing. It's going to be 2 times the vector 3, 1 minus the vector 2, 5. That's going to be, let's see, 2 times 3, 1 is 6, 2. We just distribute the scalar to each of the components of the vector minus the vector 2, 5. And then we subtract and we get 6 minus 2 is 4. 2 minus 3 is negative. Sorry, 2 minus 5 is negative 3. Okay, and we can draw that as well. So the vector, I will admit I have a hard time doing subtraction graphically. I always have to remind myself how it works, but let's do it anyway. So let's see here. First, I'm going to do 2v. So 2v is just the vector 6, 2. 1, 2, 3, 4, 5, 6. 1, 2. I'm literally just doing a v plus another v. That's 2v. Starting at the origin, ending at the point 6, 2. And then from there, I'm going to subtract off 2, 5. I'm not good at subtracting with vectors. What I would encourage you to think of instead is this is really, at least graphically, this is the vector 6, 2 plus the vector -2, -5. That's the way I'm thinking of it when I'm trying to draw it. So the vector -2, -5 is left 2 and down 5. So from there, I'm really going to go left 2. So 1, 2 and down 5. 1, 2, 3, 4, 5. That's my minus W. So my resulting vector starts there and ends there. Sorry, it starts at the origin and ends at that point there. So there's your vector 2v minus W, which seems reasonable, right? Because I'm going over 4 and down 3. So yeah, that seems right. There is a tricky way of, like, I should say, there's a tricky way of drawing it that makes it work every time that is kind of feels like magic, but no one really, that's not something we focus on in this class really. So I will just tell you, if I had drawn the vector W, sure, I'll draw the vector W so you can see it, which is over 2 and up 5. And then you connect that point to that point. That will also give you the vector 2v minus W. But I never was good at seeing that that was the same thing. So I just always did it this way, where I draw my 2v and then I do negative W and add it that way. And again, either way you see it is fine. Oh, I know what we should say though. Let's go back. Sorry, let's go back to the previous example for a second. I do want to point out, sorry, I totally meant to do this. If someone asks you to find, say, like the magnitude of V plus W, then you should add them together first. So the magnitude of V plus W, well, V plus W is 5, 6. So it's really just the magnitude of the vector 5, 6, which is just going to be the square root of 5 squared plus 6 squared, which is the square root of something. I don't know, 61, sure, 61. But there's no other way to do it really. You can't say it's the magnitude of this part plus the magnitude of this part. No, you have to add the vectors together first, and then whatever your resulting vector is, find the length of that vector, the magnitude of that vector. Similarly here, if I ask the same sort of thing in this other question, if I said, in fact, why don't you all find it? I want you all to find the magnitude of that vector 2v minus W, which we've already found the vector, you just have to find the magnitude of it. Okay, all right. Right, I think we've got it here. The magnitude here is going to be the square root of the first component squared plus the second component squared. All the things you're adding together in the square root should all be positive, right? Whether you've got negative components or positive components, when you square them, they all become positive. So the whole thing here is just going to be the square root of 16 plus 9, which is once again the square root of 25, which is 5. So that vector has a length of 5 or a magnitude of 5. All right, let's talk about three-dimensional vectors. Nothing's really different, is what I should really say. Oh, well, okay, yes, we know. Right. But that's really the big picture thing. 2 dimensions, 3 dimensions, there's really not a whole lot of difference other than you have to write 3 components instead of 2 components. But for the most part, everything works the same sort of way. There's maybe one thing that I would particularly note that feels different, and we'll get there in a minute. So we will try to draw something in the chat, one sec. Wouldn't the direction change for 2v minus W? I'm not sure what you mean exactly, Peyton. So for 2v minus W, I'm going in the 2v direction, and then I'm going in the negative W direction. So that should be 2v minus W, starting there and ending at the point through 4, -3. You're welcome to unmute and say words if you would like to, or you can type things in the chat. I'm just not sure what you're trying to ask there. Like, no, so this is definitely the correct direction. And so whether I want to draw it down here like I have, I think it is, right? I mean, if I do the subtraction, I do get the vector 4, -3. That's certainly going in the positive x direction and the negative y direction. I could either draw it there, or I could draw it starting here and ending there. It just feels kind of, and again, this is a trick I remember learning when I took linear algebra, where you can draw the vector 2v and w, and if you want to find 2v minus w, you start at w and you end at 2v, which feels kind of funky, but it does work. And we can see that it works because literally these vectors, whether I draw that one or that one, they do point in the same direction. Cool. Good, I'm glad. Because I didn't really have a better way of explaining it, so I'm glad you see it. All right, let's talk about graphing some vectors in 3 dimensions, which I don't imagine you will do a whole lot of. So we'll do like 1. 3D vectors. In this class, we mostly keep to the idea of vectors representing like things you could actually imagine in space. Like you could imagine a 3-dimensional vector that started in that corner and ended at the top of that window over there, right? There could be an arrow pointing from there to there. Technically, you can have vectors in 4 dimensions or 5 dimensions or any number of dimensions, and they can represent all sorts of qualitative things about things. But that's not us. We're talking about actual real physical interpretation, which is nice. So let's plot the vector. Sure. Do a callback to, do I remember what they were yesterday? I'll try. Do I remember what they were? I don't know. I'll just make it sure. I think it was something like 2, 4, 6. So yesterday we plotted a point in 3 dimensions, not yesterday. You know, when I say yesterday, I mean the last time I saw you all, which was not yesterday, the day before yesterday. We plotted some points in 3-dimensional space. And we might have plotted the 0.246. It might have been 426. I don't remember what it was. And I was getting 4s and 6s. That was in this class, right? We did that. Now I'm like debating. Did I do that other class? No, it was in this class. Okay, sorry. Losing my mind. Sorry. So if I want to plot this vector, well, just like I was plotting vectors in 2 dimensions, we're going to start at the origin and we're going to end the vector at that point. So in 3 dimensions here, so first we're just going to plot the 0.246. So we're going to go 2 in the x direction, 4 in the y direction, 6 in the z direction. And then we have to kind of like match them all up. So we're going here and there. And then we're going up like this. We're trying to draw the little box. Like that. And over here like that. Trying to be good about drawing things parallel to the axes they're parallel to. It looks like that's your point right there. There's the point, not the vector. That's just the point 2, 4, 6. So we use parentheses. And then the vector is the arrow that emanates from the origin and points towards that point. Right. So we're imagining it coming, right? It's not just going up and to the left, it's going forward and left and up. So like kind of from here to there, which I know is not easy for you all to see at home because it's harder to see the depth perception here, but you all can see in class, right? I'm starting like here and then going out 2, over 4, up 6. So the arrow from there to there. Should bring some string. String would be great. Oh well, I can use these chords, but that's probably not gonna work so well. What's the magnitude of V? Oh, yeah. Well, just like before, square root of the squares of all the components added together. So it's going to be the square root of 2 squared plus 4 squared plus 6 squared. That's how we find the magnitude of any vector. Take all the components, square each component, add them all together, take the square root. It's really just the distance formula. You're really just finding the distance between the origin and the 0.246, which is just 2 minus 0 squared plus 4 minus 0 squared plus 6 minus 0 squared, the square root of all that. Here we end up getting, let's see, 36 plus 16 plus 4 is 56. Squared 56. Could you simplify that? Yeah. Meaning there is a square factor of 56. 4 is a factor of 56. You could, if you felt compelled to, write this as 4 times what, 14? 56 divided by 2 is 28, divided by 2 again is 14, so yeah, 14. And then write that as 2 times the square root of 14. I don't think you need to do that. A couple other things about this. So you could write v this way. You could also write v as the vector 2i plus 4j plus 6 ij. Okay. Sometimes people draw little arrows over these ij and k's. Usually we don't though. So just like before, so I is still a unit vector in the x direction, meaning it's a vector that's 1 in the x and 0 in the other. But if you're working in 3 dimensions, you have to write the unit vector I as the vector 1, 0, 0. And the unit vector j as 0, 1, 0. And the unit vector k as 0, 0, 1. These are unit vectors, right? They all have a length of 1. If you found the magnitude of any of these vectors, it would just be the square root of 1 squared plus 0 squared plus 0 squared, which is 1. So all of these unit vectors, I should say all of these basis unit vectors have a magnitude of 1. The reason I'm calling them basis vectors is not really important, but I know your teachers are going to throw that word around. It just means they're the ones we typically use for our 2-dimensional or 3-dimensional coordinate system. If you ever take linear algebra, come back and ask me about it, because there's more to it than that, but most of you probably aren't going to take linear algebra, so I'm not going to sweat it for now. Something else I was going to say here. No, I don't think so. Maybe not. Sure. Let's find the unit vector. So the unit vector in the same direction as A. Sorry, V, pardon me. It's the same process as it was before. You're still just taking your original vector, dividing it by its own magnitude. So that's going to be V divided by the magnitude of V. And you will see this notation a lot. People aren't just going to write U, and they're going to write vector divided by its own magnitude. And then that's just going to be the vector 2, 4, 6 divided by the vector, or sorry, the scalar square root of 56. And again, I like it like that, but people would probably write it as 2 over root 56, comma 4 over root 56, comma 6 over root 56. Yeah, let's do, yeah, we got enough time. Let me show you an example that I think is going to be super helpful to you in life in general. Let's look at this example. I want to find a vector of length 3 or magnitude 3, if you prefer the word magnitude, in the same direction as W equal to 1/17, comma, -4/17, comma, 2/17. That is super annoying. But the thought process here is not super challenging. Here's what we're going to do. You're going to take your vector, which gives you the direction. You're going to divide it by its own magnitude, which will give you a vector of length 1 in that direction. And then we're going to multiply that by 3. If you take a vector of length 1 and multiply it by 3, you get a vector of length 3. So everyone pause for a second. Don't write down anything I'm about to write down, because what I'm about to write down is trash. So here's how you could do it, which you should not do it this way. You could do, so one answer, which is correct, but again, I'm going to point out is not nice, would just be to do 3 times the vector W divided by the magnitude of W. If I write this down, you should not write it down. You get this grossness. You get 3 times this vector divided by the magnitude of that vector, which is the square root of 1/17 squared plus negative 4/17 squared plus 2/17 squared. And that's something. And yes, if you really, really want to, you can write it down. I won't stop you from writing it down. But let me tell you, there's a better way. Do you know what other vector points in the same direction as that vector? That vector. That vector points in the same direction as W. And so if I want to find a vector that also points in that direction, that has a length of 3, well, instead of normalizing this vector and getting a vector of length 1 in that direction, let's normalize the much nicer looking vector and get a vector of length 1 in that same direction. So V divided by the magnitude of V is the vector 1, negative 4, 2, divided by the square root of 1 squared plus negative 4 squared plus 2 squared, which is the vector 1, negative 4, 2, divided by 16 plus 4 plus 1, square root of 21. That's a lot less terrible to write that. Now we're not quite done. This is a vector of length 1. I should just write unit vector. It's stupid to write a vector of length 1. It is a unit vector in the same direction as W. Great, let's multiply it by 3. So our nicer answer is 3 times V divided by the magnitude of V, which is just 3 times 1, negative 4, 2 over the square root of 21. Which you could then, if you really felt compelled to, a lot of compulsion going on over here. You can write this as the vector 3 over root 21, comma, negative 12 over root 21, comma, 6 over root 21. And if you started with this and worked really hard, you could make this look like that. But why work really hard when you don't have to? Which is kind of the theme of every class I teach. Why work really hard to do something when there's a nicer, easier, just as good way of doing it? So the point here is really the following. If they give you a gross vector where all the components have the same denominator, or really any denominator, you can find a common denominator for, instead of finding the unit vector for that, you can multiply that by anything you want and then find the unit vector for the new thing, because both of those vectors point in the same direction, right? If I drew this, I'm going to draw it in 2 dimensions because I'm bad at drawing in 3 dimensions. Here's the tiny vector W I'm pretending. And here's the vector V that's 17 times as long as it. And you know what? The unit vector for either one of those vectors is the same because they both point in the same direction and they both have the length of 1. It's a nice trick. It really is a useful thing to be able to do. Okay. We got 5 minutes left. Sure, yeah. There's so many things to talk about there. Have you guys talked about the dot product yet? Okay, let's talk about the dot product for a second. That's a good place to end. So the dot product of 2 vectors. The dot product. There are 2 ways of calculating the dot product between 2 vectors. One that's easy, one that's not, but both are useful. So for, let's say, do I want to make something nice? No, not really. Yeah, I kind of do. Sure. Let's say our vector V is the vector 3, 0, and our vector W is the vector 4, 4. One way to calculate the dot product, the easy way, the dot W, and make sure you emphasize the dot there, right? Don't just write V next to W, you really need to write a little dot symbol there. It's going to equal the component, the corresponding components of V and W multiplied together and added up. So it's going to be 3 times 4 plus 0 times 4, which in this case is going to be 12. That's the usual easy way of calculating the dot product of 2 vectors. But another way of calculating the dot product of 2 vectors, which should give the same result, is that it's equal to the magnitude of V times the magnitude of W times cosine of the angle between those two vectors. Which is why I picked these vectors, because the angle between them is easy to find the cosine of. So if I draw these two vectors, let's take a look. So V is the vector that's just 3 to the right. So it starts there, ends there. There's your vector V. And W is the vector that's over 4 and up 4. And who would like to tell me the angle between these two vectors? Well, everybody? Everybody wants to tell me? What's the angle there? Between the horizontal axis and the line y equals x? How many degrees? Yeah, it's 45 degrees, right? Y equals x makes a 45-degree angle with the x and the y axis, actually. So that's a 45-degree angle, or pi over 4 radians. So check this out. The magnitude of V, I guess we could write up here, the magnitude of V, if only one of the components is not 0, the magnitude is just the absolute value of that component. So the magnitude of V is just 3, but we can calculate it. It's the square root of 3 squared plus 0 squared, which is the square root of 9. The magnitude of W, be careful. People make the mistake of saying the magnitude of W is 4. It's not 4. It's the square root of 4 squared plus 4 squared, which is the square root of 16 plus 16, which is the square root of 32. You can simplify that if you really wanted to as 4 root 2. I don't really want to, but I did. So here we get the magnitude of V, which is 3, times the magnitude of W, which is 4 times the square root of 2, times cosine of pi over 4. And cosine of 45 degrees, or cosine of pi over 4, is root 2 over 2. And root 2 times root 2 is just 2, and 2 over 2 is 1, and 1 times 4 times 3 is also 12. The same. So, dot product. And how much time? No, I don't have time for the whole page. Let's just write it down. So for the dot product of U and V, V and W, if V is equal to the vector V1, V2, yeah, you could have, let's say V3, and W is equal to the vector with components W1, W2, and W3, then you can either calculate V dot W as V1 times W1 plus V2 times W2 plus V3 times W3, or you can calculate it as the magnitude of V times the magnitude of W times cosine of the angle between them. And it's useful to be able to go back and forth between them, especially because knowing that the dot product is equal to this and this then allows you to find the angle between two vectors if you know what the components of those vectors are. So we can calculate that, and that, and that, and then say cosine of theta equals that divided by that, and then find theta. That's something we will probably do. I think I'm done. I feel like there's something else I want to say here. There's a word, this thing. I don't know. There was something else that was, I know what it was. The dot product is also called the scalar product, because when you take the dot product of two vectors, you get back a scalar number. You don't get a vector back. On the other hand, there's something else called the cross product, known as the vector product. And when you take the cross product of two vectors, you get a new vector back. And we'll talk about that probably on Monday. So I know there's a question about finding like a perpendicular plane to a thing, which has to do with the cross product. So, all right, have a lovely weekend. I will see you on Monday if you're here, or you'll see me on the video if you're not here.